Welcome back, everyone. We're very happy to have with us Diane Maclagan from the University of Warwick, and to give us an update on tropical schemes. Over to you, Diane.
Okay, so thank you. Thank you for the invitation, and I think this is one of the real silver linings of the last few years, that we can actually bring people together around the world and expect it to actually work now. So I hope that we manage to keep this connection across continents going forward. So on a non-mathematical note, any lack of, for those who don't know, Warwick is in the UK, so any lack of polish you can blame on our interesting politics from the last 24 hours. The time I should have been spending proofreading my slides. Okay, so I'm going to give you an update on tropical schemes, but let me start with telling you what do I mean by this world. I mean, we have a slogan in tropical geometry that tropical geometry is algebraic geometry over the tropical semi-ring. And we're always a little vague about precisely what that means. I should say, just as a notational point, for me, I will write R bar for the tropical semi-ring. I will be using the min convention. So that means R bar is R union positive infinity with the operations tropical plus, which is minimum, and tropical times, which is usual addition. So the goal of the talk is to introduce tropical schemes and update the status of the program. So this is a program that has been ongoing for about 5 years or so to develop some of the algebraic foundations of tropical geometry. And I'll say more about what I mean by that as we go on. I think when I first gave the title, I thought maybe I'd focus more on the update, but for the talks I've been able to get to, looking at who the audience was, I thought maybe it made more sense to focus on introducing it. And so I do really ask, please do ask questions and interrupt me if there are things that I'm glossing over too quickly. And I have the chat up, but just if you can interrupt, that would be great. Okay, so let's come back to the basics. So we start, from this version of tropical geometry, I'm going to start with a variety. So on the left here, we see a picture of an elliptic curve. On the right, we see a tropical elliptic curve. So the idea is always we start with a variety, we tropicalize it, and following the convention, I'm going to start with a subvariety. For this talk, in my examples, I'm going to start with subvarieties of an algebraic torus over a valued field K. So we've got X contained in K star to the N, where K is a valued field, and then trop X is the set of W in R to the N, where the minimum in trop F of W is achieved at least twice for all F in the ideal of X. So I think I'm missing some, that's meant to be a Laurent polynomial ring there. So there's a typo here that I should have Laurent polynomials here since I'm focusing on the torus. So here we have the tropicalization of X is, I just start with a polynomial F, usual polynomial F, and I tropicalize it by turning addition into tropical addition, multiplication into tropical multiplication, and taking the valuation. Sorry, that should be, there's another typo, it's not good. That should be the valuation of my coefficient AU. So CU here is the valuation of AU. And so the idea here is we do this operation, we take the locus where the minimum is achieved at least twice, and this gives us our tropical variety. Hopefully this is familiar to everyone in the audience after almost 2 weeks of talks on the subject. The thing we know here is that when we do this, we get a space with a lot of structure. Okay? The tropicalization of X is the support of a polyhedral complex. You can see here my picture on the right is a union of polyhedra. And then there's more structure, right? If X is irreducible, this should be connected. In fact, it should be connected, where D is the dimension of X in a certain sense. It satisfies combinatorial constraints, the balancing condition, which we'll talk about later. And the idea is that it should encode some information about the geometry of X. At a minimum, if I have a projective variety, it should be the dimension and the degree, and then often more. For example, we know that the lattice length of the cycle in this picture is the negative valuation of the J invariant. Okay, so that's the story from maybe the first decade of tropical geometry, that we understood this information. But I should emphasize that it is somehow a variety story, or maybe a cycle story. So when we think of these not just as sets, but coming with multiplicities, as we'll discuss a little bit later, and then we get tropical cycles. So this is something that, at the variety level is recognizable to a 19th century algebraic geometer. Cycle level, we're getting to the early mid-20th century. And so there's been a lot of algebraic geometry in the last 50 years. And I think one of the goals of this program is to let us use more of those techniques in tropical geometry. Okay, so that's where we're going. But let me first point out the other theme of this talk is that we want an intrinsic tropical geometry. So there's two things you could do in this world, part of the subject. You could tropicalize objects, or you could try and talk about objects inside tropical geometry, prove theorems purely in tropical geometry, and then from that, they've lifted up to theorems in algebraic geometry. So we would like a scheme theory that makes sense inside tropical geometry. But so let's start by observing that for varieties, this somewhat makes sense. If I start with an ideal in the semi-ring of tropical polynomials, so this is it's a semi-ring, I just write down polynomials with coefficients in the tropical semi-ring, and I expect every operation should be tropical. So addition should be tropical addition, multiplication should be tropical multiplication. So these tropical polynomials are really, as functions, they're piecewise linear functions, but I want to think about them as elements of the semi-ring. I can start with an ideal here. So that just means closed under addition, closed under multiplication by elements of my semi-ring. And from that, you get a variety in the same way. We just ask for the minimum in f of w to be achieved at least twice for all f in your ideal. So here f is a tropical polynomial, so it's a tropical sum of some terms, so that means in usual arithmetic it's the minimum of some terms, and we want those minimums to be achieved at least twice. We don't want, it's a minimum of a bunch of things, and we want that minimum to be achieved in more than one term for the value w. And that's our set of w. And you can note that if I start with a subvariety of a torus, then the tropicalization of X is just the variety of the tropicalization of I. So by the tropicalization of I mean the ideal in the semi-ring of tropical polynomials, or Laurent polynomials here, generated by the tropicalization of all polynomials in the ideal. And I should, and this is just a restatement really of the previous definition. So our usual way of thinking about the tropicalization of a variety, we want the minimum achieved twice in each tropicalization. We could instead say we're going to first tropicalize the ideal of, and I here is the ideal of X, the ideal of all Laurent polynomials vanishing on X. I can first tropicalize the ideal of X and then take its variety, and I'll get the same thing. So that's just rearranging the definition. Okay, so that's well and good. So it looks like at least at varieties, we can talk about things in a more algebraic language. There are some issues though. Okay, so this is just repeating the definition at the top of the slide. Well, actually, sorry, maybe I should have paused for any questions about this definition in here, or questions or comments.
I have a question. It's not exactly about the definition. I was wondering, do nilpotents play any role in this?
Yeah, no, that's an excellent question. And maybe ask this question again in a few slides when I come back to this, because this is exactly one of the points, right? Is that so far the story I've been telling you for variety, well, maybe let's say for varieties, the answer is no. Okay, if I take the ideal, if my original ideal before I tropicalized was generated by x squared or x, I'm going to get the same variety. It's just going to be a set theoretic thing. As cycles, you're going to see a slight difference. So maybe if I come back to my picture, if I had taken this, in this picture, I would put multiplicities 1 on every edge. If I instead took the equation for my elliptic curve and squared it, the only way I would draw the same picture, I might put 2s on every edge instead. So I would get a slightly different cycle, but I wouldn't be able to tell the difference between different ways of having nilpotents, so different non-reduced scheme structures from the pictures I'm drawing here. Okay? And that is exactly one of the things that we're trying to fix with this theory.
I think there's another question.
So in the next slide, can you go to the next? What is the valuation on R closure that you want to define so that you can tropicalize? I mean, or R closure is it a real?
So here, you mean here?
Yeah, yeah.
Right. So here you'll notice. So here, let me make a distinction. Here I had to say trop F. Sorry, my highlighter's not working. Here I had to say trop F of W. Here I'm just saying F of W. Okay, I don't need to take evaluation because I already have a tropical polynomial. Okay, I'm starting with an ideal in the semi-ring of tropical polynomials. So its coefficients are already elements of the tropical semi-ring. The polynomial itself is already a minimum of things.
Okay. So what is R closure defined? How is it defined? R closure, if it is all.
So this is my notation,
okay,
right?
okay.
It's my yes, right. Yes, that was the answer. I see, that was the question. Yeah, it's not a closure of the real numbers. This is my notation for the tropical semi-ring, right? So the operation, whenever I have R bar, the operations are tropical operations.
Okay. Thank you.
So that's my signal for what some people call T. Might use black bold T or.
Thank you.
Yeah. So it's, for me, the bar is reminding me that we have an infinity there. Okay, more, and Phil, yeah, please do interrupt with question. Yeah, don't wait for me to ask. Okay, so what we've got here is the idea we just said. We've got my semi-ring of tropical polynomials, so an ideal with coefficients in the tropical semi-ring, and we're looking for W and R to the N, where the minimum is achieved at least twice. So that's my varieties, and that looks like a perfectly good definition, but there's some problems. Okay, so the first problem is that the variety of I is not always the support of a polyhedral complex, right? Once you see enough talks in tropical geometry, you know that if you're on this embedded side of tropical geometry, where we're tropicalizing subvarieties, you always see polyhedral complexes. But this does not always happen in this world. So the issue here is you can get things like a disk inside a hyperplane. So let me give an example, give me some idea of what that is. So maybe this is also just a warm-up for how I'm thinking about varieties for anyone for whom this is new. Suppose I had this half space. So I have the set of X such that A dot X equals B, C dot X is greater than or equal to D. So here, X is a vector, A and C are vectors, B and D are numbers. So this is a hyperplane, and then I'm intersecting it with, I'm taking the positive half of another hyperplane. So it's a positive half hyperplane. Now this is the variety of the set of the following two polynomials. If I take the ideal generated by x to the a tropical plus b and d minus b tropical times x to the a plus tropical plus x to the c tropical plus d, and I ask, what is the variety of this? Well, if the minimum is achieved at least twice in x to the a plus b, x to the a plus b as a function, that's the x to the a is, that's x1 to the a1 tropical times x2 to the a2, etc. That's just x dot a. So this is really the minimum of x of a dot x, and b has to be achieved at least twice, or in other words, we have to have of a, oops, the highlight's not working. We have to have a dot x equals b here. Okay, so if you're in the variety of this equation, you have to have a dot x equals b. And then once you know that a dot x equals b, here we have to have the minimum achieved twice between d minus b plus a dot x, c dot x, and d. Okay, but a dot x equals b, so this equals d. D minus b plus a dot x is d minus b plus b is d. So I have the minimum is achieved at least twice between d, c dot x, and d. And so the only way that's possible is if c dot x is greater than or equal to d. Okay. So what are we seeing? We're seeing that a half hyperplane is the variety of an ideal in the semiring. Okay, that's fine. Why is that a problem? Well, if I take my circle in the plane, I can just take all of the rational supporting hyperplanes and add the equations for those, and the ideal derivative by all of these equations is going to cut out a circle.
I have a question. Yeah. So here, when we take the zero set of xa plus b, so how can we say that the minimum is achieved twice when a dot x is equal to b? As in, why are we?
Okay, sure. So let's think about what x to the a means as a function, as a tropical function, right? It's x1 to the a1 tropical times, and what does x1 to the a1 mean, right? It means x1 tropical times x1 tropical times x1 a1 times. In usual arithmetic, that's a1 times x1.
Yeah.
Okay? So it's x1 to the a1 times x2 to the a2, right? A is a vector here, right? Times x2 to the a2 up to xn to the an. So in usual arithmetic, that's a1 times x1 plus a2 times x2 up to an times xn. So that's a dot x. So as a function, x to the a is a dot x.
Yeah.
And so we want the minimum to be achieved twice at a dot x and b. The only way that that can happen is if they're equal.
Oh, all right. Yeah.
Yeah.
So that'll
Thanks.
That'll happen when both of them are equal, right?
That's right. Yeah. It's because the minimum being achieved twice, that means two of the terms are equal and they're less than or equal to all of the other terms. Okay. Great. Thanks. Yeah. Any other questions before I move on to this?
They don't seem to be any at the moment.
Okay, great. So what have we got? We have the point of this example in blue was that we get any half hyperplane as the tropicalization of an ideal. And now what I can do is I take my circle in a plane. I take my favorite plane a dot x. I take a circle in that plane, and I throw in all of the supporting hyperplanes, and that lets me. And I add those equations to this ideal. That'll be an infinite number of equations, but I take the variety the ideal derivative by all of those. I take its variety, and that will give me the circle. Okay, so we're getting things that are not polyhedral complexes. Okay? And from the point of view, I mean, some of the power of tropical geometry over the last 20 years has been precisely that we've turned complicated questions in algebraic geometry into simpler combinatorial questions. So this is a potential problem. Okay. On the algebraic side, where we're seeing the problem is that this is meaning that this is coming from the fact that ideals are not always finally generated. One of the most elementary things in affine algebraic geometry is the fact that the polynomial ring is Noetherian. And what we're seeing is that the semi-ring of tropical polynomials is not Noetherian in this sense. Okay, so we're claiming, and this is following, I mean, this is implicit when I'm telling you, if I just keep on throwing these equations in, we're going to cut out more and more things. So that ideal is not finally generated. But we can see this on a simpler example. If I just take the semi-ring of tropical polynomials in one variable, x, and I take the ideal generated by x plus 0, x squared plus 0, x cubed plus 0, and so on. So just x to the n plus 0 for all n. I claim that this is not finitely generated. Okay? And this is precisely because the tropical semi-ring has no subtraction. Okay? So why is this? Well, let's think about it. I take x plus 0, and I imagine, first of all, this does not generate x squared. Your x squared plus 0 is not a multiple of that. Why? Because if any multiple of that, of x plus 0 that contains x squared, well, I'd have to have x times this, but then I'd have to have an x term. Okay, so there's no way to get rid of the x term. So I need at least x plus 0 and x squared plus 0, but now we keep on making the same argument, right? If you're going to have an x cubed, a polynomial involving x cubed in the ideal generated by x plus 0 and x squared plus 0, then you would automatically get at least an x or an x squared term. So there's no way to get a polynomial that has an x cubed term and no x and x squared term in the ideal generated by the first term. And then you can just check that this keeps on going. And this is somehow precisely because there is no subtraction, right? If I get a term in a polynomial in some sum, I can't then remove it with subtraction. And what this gives us is that the semi-ring of tropical polynomials is not Noetherian. Ideals are not always finally generated. And that's behind some of the difficulty in this theory. Okay, and we'll come back to these problems later. So maybe I should pause questions on that.
These half spaces also don't show up as tropicalizations, right? Do they?
That's right. No, exactly. These are not the tropicalization of a variety. And you can see this because you know that, I mean, one way to see this is that they're not balanced.
Yeah.
Right. Yeah. Yeah. So, I mean, tropicalizations have to satisfy this balancing condition, and a half hyperplane is not balanced. Yes. Exactly.
Thank you. Yeah.
Yeah. So, exactly. So we're getting more than just tropicalizations. And that's either a bug or a feature, depending on your point of view. And maybe I'll say something more about that later.
But we could just lift these two equations to some polynomials, right, over a valued field. But that's then there will be some cancellations, and that'll introduce some new elements in the tropical basis. No, that's probably what
exactly.
will happen.
Yes, exactly.
Okay.
Yeah, if you think about it, exactly. So if I lifted it, we would throw away more things. And this is maybe not so shocking, right? If I lifted it, you would expect to get something codimension 2. And here I'm getting something that looks like it's codimension 1. So you'll get a codimension 2 thing inside this half hyperplane.
Yes, thank you.
Okay, great. So let's come back now to the main theme. This is the main theme of this is meant to be, we're going to define subschemes of tropical toric varieties. So I should say, I'm going to say toric varieties, just so you know that it exists, and I'm happy to talk more about the details, but it turns out that I can tell you everything, all of the details and all of the difficulties lie in even thinking about subschemes of the tropicalization of the torus. So I'm going to focus on that on my slides. I'm happy to answer, and I'll say a few words later about how this generalizes to toric varieties, and I'm happy to answer questions there. But let's come back to sort of thinking about what do we mean when we talk about so right, for the next few slides, we're just going to think about affine schemes. We're going to have a sub-scheme of the algebraic torus. Okay, so that's given by spec of the quotient of the Laurent polynomial ring by some ideal J. Okay, so I have some ideal J, and this is where the tie in with the previous question about nilpotents. This is where, now that we're talking about subschemes, we want to allow the possibility that J is not a radical ideal, that we do. So the ring that we're taking spec of now may have nilpotents. Okay. So when you start to think about how to tropicalize, the first steps are fairly straightforward. Okay, we've known since the start of tropical geometry pretty much that if I want to tropicalize my Laurent polynomial ring, I should replace it by the semi-ring of tropical polynomials that you've seen on the previous slides. And it's been implicit in my last few slides that if I start with an ideal here, I should tropicalize it to an ideal in the semi-ring of tropical polynomials. So you might think of I as the tropicalization of J, or in principle, we might start with any ideal I there. And I'll remind you, as I said in the previous slides, in a semi-ring, ideals are defined the same way as they are in rings, right? So just closed under addition and by multiplication by elements of the semi-ring. This is one thing when you start to think about the algebra or the commutative algebra of this world, you have to ask yourself, what are the definitions still? Are they still valid? Okay, so this much works fine. Okay. The next step we have to change slightly, but this is something that has been maybe well understood by people working in semi-rings for a long time. The first question you ask yourself is, why do we think about ideals in basic commutative algebra in the first place? Okay. We think about ideals because they are the kernel of homomorphisms. When you're in a semi-ring, the kernel of homomorphism, the thing that's sent to the zero of the semi-ring, which is infinity for us in the tropical semi-ring, is not as useful. What you want to know really is, in your homomorphism, which things are sent to the same element. And that suggests that what we really want to think about here are congruences. So these are equivalence relations on the semi-ring that are compatible with addition and multiplication. So if A is congruent to B, that means A times C is congruent to B times C, and A plus C is congruent to B plus C for any A, B, and C in my semi-ring. And the reason we want this is that this is what we can take a quotient by. What you're doing is you're remembering in your homomorphism which things are identified. So we take the quotient by congruences. So congruences are something that have been maybe well understood by people who think about semi-rings for a while. The new ingredient about maybe 5-ish years ago from Jeff and Noah Giangiracusce was to choose the correct congruence that makes sense in tropical geometry. And that's what I want to tell you about next. So the idea is as follows. If I have a polynomial in the semi-ring of tropical polynomials, so I've written it here as a tropical sum of Cu tropical times x to the u. So Cu here is an element of my tropical semi-ring. I'm going to form the relation. I'm going to take a term x to the v that shows up. I'll form the polynomial f v hat, which is just I remove of the term involving v from my polynomial f, and then I set f is congruent to fv hat. And I'll do some examples of this on the next slide. Okay, but the idea is you give me an ideal, I form this congruence by, well, for every polynomial, I set it congruent to the polynomial with terms removed. Okay, so this is just the same definition at the top here from the previous slide. So let's see an example. So the first example will be if I start with x plus y plus 0, then I just set x plus y plus 0 congruent to x plus y, that's with the term 0 removed, congruent to x plus 0, that's with the term y removed, and congruent to y plus 0, that's with the term x removed. Okay, so this gives, and then if I have an ideal, the bent congruence of I is I'm just going to do this for every polynomial in the ideal and every term of that polynomial. So I'll get, and then I take the congruence generated by this. And I mean, if you've never thought about congruences, you might think, well, does that make sense? And I reassure you that it does. So the point is that, so we take all of these equivalence relations, and then we take the congruence generated by, that means we take the transitive closure, et cetera, to make it an equivalence relation, and then we take the closure under addition and multiplication. Okay. Once you have that, you have something that you can take a quotient by. Okay. So, because congruences are the things you can take quotients by. So maybe questions about the definition before I give the motivation.
In this definition, if you have a monomial, and this not monomial, but if you have a term like x plus y plus 0 or any term like that, then it finally, will it be eventually congruent to one particular term of it? And
no, okay. I only do this for the polynomials I start with. Okay, so I don't take x plus y and make it congruent to x now. I only do this I only remove it from the polynomials in the ideal to start with. So I'll remove one term, but I don't then remove another term and another term and another term.
Ah, okay, okay. Oh, I see. Okay, okay. Thank you. Yeah.
Okay.
Hi, sorry, can I ask a question? Oh, I can't. Hi, so sorry, maybe I misunderstood the definition. So before you do the congruence, you may have different polynomials, which are different polynomials, but same as functions. But when you do this congruence relation, you are identifying two polynomials, which are different functions. I mean, maybe
is that the,
like
yes.
x plus y plus 0 and x plus y.
Right. Right. So suppose you have to ask yourself which polynomial is in the ideal to start with, right? So suppose we had x, was your example, was it x squared plus x plus 0? Suppose I had x squared plus x plus 0. I would set that congruent to x squared plus 0, which is the same as a function. But I would also set it congruent to x plus 0, which is different as a function.
Right, but x squared plus x, would you also set it to congruent to x squared plus x?
Yeah, and also to x. So I would set x squared plus x plus 0 congruent to. I would take all three terms and set it congruent to removing either. So it would be congruent to x squared plus x. It would be congruent to x squared plus 0 and to x plus 0.
I see. But as a function, then x squared plus x is not same as x squared plus x plus 0, right?
That's true, yes.
I see.
Okay. So as functions, they're different. But here's the key point, and this is getting into the motivation. At a point where the minimum was achieved at least twice, they agree, right? The key point of if you have a point at which the minimum is achieved twice, when you remove one term, you haven't changed the minimum. So it sounds, so as functions on the whole r to the n, you've changed them. but on the locus of the tropical variety, you haven't changed them. And that's the key idea. Yeah,
okay, thank you. Thanks.
Yeah, so let me say that, okay, right, the key idea here, and this is the motivation, is that what we're setting equal are polynomials that agree on the variety. They're different as functions, but they agree as functions on the tropical variety. Okay, and that is because if the minimum is achieved at least twice, you remove one of the terms, you're getting the same minimum value. Okay. A different way to say the motivation is if I take the R bar valued, you should think about this as taking the R bar valued points of the scheme that I haven't defined yet. If I take homomorphisms as semi-rings from this quotient to R bar, this is the same as the variety. In what sense? Well, a homomorphism from this quotient, that's going to be defined by the values I give to x1 up to xn. And if I take that vector, well, saying that we've quotiented by this congruence, that's exactly saying that I have to send f and f to the v hat to the same place. Okay, so that means that that means f of w has to equal f of v hat of w, which means that the minimum must have been achieved at least twice. Well, the minimum was not achieved uniquely at x to the v in f, so the minimum was achieved at least twice. Okay, so the idea is here that I recover the variety from the bend congruence. So this bend congruence knows about the variety. Okay, that's the point of this definition. So, okay. So the definition then, this is tropicalizing scheme. So this comes from, there's a 2 here because this is from a theorem of, or definition of Jeff and Noah Giangiracusce, so mathematical brothers. They define the tropicalization. If I start with a subscheme X of the torus, so given by spec of the quotient of the Laurent polynomial ring by an ideal, then the tropicalization of X is going to be, we're going to define it to be, I take the quotient of the semi-ring of tropical polynomials by the bend congruence, and then I take, that's a perfectly good semi-ring, and now I'll take spec in the sense of F1 geometry. There's a general theme in tropical geometry that some of the important technical tools we needed were developed in the 20 years before. So, well, here, many of you know, for example, the Berry-Groves theorem that tropical varieties are polyhedral complexes predates tropical geometry by 20 years. There's a bunch of examples of this. And one example is that people had been working on extending the definition of schemes to semi-rings over the last few decades. And this loosely fits under the umbrella of F1 geometry. So this is the not well-defined concept of geometry over the field with one element. And I think the main reference I would give, if you're interested in this in the context of tropical geometry, I would point you to the work of Oliver Lorscheid. So he's developed a whole framework that fits in well with this world, and sort of theory of blue schemes and explaining how this fits with tropical geometry. So that's the definition.
So the quotient, so how are you taking the quotient here? So again, the quotient with the ideal.
We start with an ideal,
yes. We
tropicalize it. So now I have an ideal in the semi-ring of tropical.
Yes.
Now I form the bend congruence, right? So the bend congruence was exactly this thing that we defined on the previous slide. I told you which polynomials to set congruent to each other. And now, once I have a congruence, I can take a quotient, okay? Because a congruence is just telling you what things shall I identify.
Right.
And the point of a congruence, this is the reason for this definition, right? The point is it's compatible with addition and it's compatible with multiplication. So when you take a semi-ring, you are quotient by a congruence, you again have a semi-ring.
Right.
So yeah, that is the point of congruences.
Oh yeah, thank you.
Does that make? Yeah. Right.
Yeah.
So what have we done? We've started with a subscheme of the torus. I have tropicalized used the ambient coordinate ring. I've tropicalized the relations that are given by the ideal J, and then I've taken spec in the sense of F1 geometry. So this is now some topological space with a sheaf of semi-rings. I won't go into the details of that, because what I want to focus on for the rest of the talk is somehow in the same way that for affine algebraic geometry is really commutative algebra, or we can focus on just this quotient in order to understand what's going on. Sorry, was there another question?
Yeah, so could you just re-explain why that in the previous slide? Yeah, so I don't understand why home of that is isomorphic to VI. I mean, is
sure
bijective to VI.
Right. So I think about homomorphism to R bar is determined by what it does to x1 up to xn. Okay, so if I'm going to give you, think about this. It often helps to think about this. Replace R bar by a field K and B of I by an ideal. All first, if you think then, so this homomorphism is determined by what it does to x1 up to xn. So I'm going to take the homomorphism to just that vector of phi of x1 up to phi of xn. And now let's think about what does it mean to quotient by, if it's a homomorphism from the quotient by this congruence, that means that whenever f is congruent to f v hat, I had better send phi of f had better equal phi of f v hat. Okay. And now phi of f, so phi of f is really, I just plug in phi of x1 up to phi of xn into the polynomial f, and I get some element of R bar. So yeah, the key point is that phi of f is f evaluated at this vector. And what we're saying is that if these are the same, the minimum has to be achieved at least twice at this point, and that's the definition of V of I.
Okay, thanks.
One more question. So in the tropical case, when you take the spec, the next spec, so in the usual case, it's the set of all prime ideals. But in the tropical case, in the sense of F1 geometry of Lorshade, what does it mean actually?
So again, well, this is something that I think that we probably deserves to be revisited. But in the formulation, again, you can take all, you can form a topological space by taking all prime ideals in the same way. It's not clear that this is this doesn't fit with some of the things I'll tell you later. So I think it needs to be revisited. But the formalism that exists at the moment is you get the topological space by taking all prime ideals and getting the sheaf of functions in the way you would expect. There's this funny phenomenon in this part of the world that some things you just you open Hartshorne and you just read the next page as if it was all tropical, and some things just work and some things don't work. And to first approximation, you can think about this as write down what you want it to be. Write down what you want to be true, and it will work. Okay. So that's the definition of tropicalizing. It would be tempting at this point to just replace the tropicalization of J by an ideal in the semi-ring of tropical polynomials. The problem with this is what I mentioned before, right? That we don't want something that we want schemes should have underlying varieties, and those varieties if it's going to be useful to tell us anything about algebraic geometry, should look like the tropicalization of varieties. So we'd like to get polyhedral objects, and we know already that if I take an arbitrary ideal here, so this means instead of saying trop J, I'm just going to say, the bent congruence of I, if I do that, then my variety might not look like a tropicalization. Okay, so that's the problem. So the solution is I'm going to restrict the class of ideals allowed. So here's the key definition of the talk. This is the definition of a tropical ideal. So the idea is that a tropical ideal is a special ideal in the semi-ring of tropical polynomials. So I don't want to use the word tropical ideal for all ideals here, only for ideals that satisfy the following condition that I'm about to tell you. Okay? And this condition is, if we're secretly going to put, so the problem, I guess, with that causes all of the issues we saw before was that the tropical semi-ring does not have subtraction. So we're going to secretly put back subtraction into this story. And this is the way it works. It looks a little weird the first time you see it, but bear with me. I'm going to put the condition that for my ideal, for every f and g in the ideal, that have the property that the coefficient of x to the u is the same in both f and g. So you might imagine, f is, if x to the u was x squared y, maybe f is 3x squared y plus some other stuff, and g is 3x squared y plus some other stuff. So whenever we have these two polynomials in the ideal, and they agree on a coefficient, then there should be another polynomial in the ideal where the coefficient of x to the u is infinity, which is our tropical zero, and all other coefficients are at least the minimum of the coefficient of f and the coefficient of b. So and they should, I guess, technical addition that they should be actually equal if the minimum, if the coefficients are different on f and g. So I'll say some more about this on the next slide. So maybe rewrite this. I want to sort of put in a side remark here that this is secretly the vector elimination condition for evaluated matroids. Okay. One of the themes of tropical geometry is that whenever you have a linear space, whenever you have a subspace of a vector space, when you tropicalize, you should get something that comes from matroids, or more generally evaluated matroids. And this is one of the axioms of the theory of evaluated matroids. And we've seen, well, we've been reminded this week with, I guess, Junhu's Fields medal that the connection between matroids and algebraic geometry is very deep and interesting. And I think this is another place where we're seeing a connection. Yeah. So so at the top here, I've just repeated this condition. Whenever f and g have the same coefficient for some term, there's a polynomial h in the ideal that has, that coefficient is infinity, and all other coefficients are at least as large. The motivating example for this definition is if I start with the tropicalization of an ideal. So then my polynomial f and g might be the tropicalization of polynomials capital F and capital G. If their coefficients of f and g are the same for some term, that means the valuations of their coefficients are the same, but you can scale, then you could choose your lifts, capital F and capital G, so that the actual coefficients are the same for capital F and capital G. And then if I want a polynomial that doesn't have that term, I just take the difference. So then H would be the tropicalization of F, capital F minus capital G, where capital F and capital G are lifts of my polynomials F and G back to the original polynomials, Laurent polynomial ring, set up so that they have the same coefficients for x to the u. And then this extra condition on the coefficients of H, this just comes from the evaluation axioms for the valuation of a sum or a difference. And so what we're saying here is that this condition, this extra elimination condition that we put on for tropical ideals is always satisfied by the tropicalization of an ideal. And this is precisely because behind the scenes, this is precisely because of this evaluated matroid condition. So you don't have to know what evaluated matroid is to at least understand this definition here. Okay. And then that lets us define a subscheme of the tropical torus to be, I mean, it looks like the previous page. We just go spec in this F1 theory world of the quotient of the semi-ring of tropical polynomials by the bent congruence of I when I is a tropical ideal. So I only want to think about this in the case where I satisfies this extra tropical ideal condition. And there are variants of this for subschemes of tropical toric varieties. So I've been telling you the story for subschemes of the tropical torus, but you are free to replace the torus here by any tropical toric variety, so any tropicalization of a toric variety. If you wanted affine space, you would just replace the Laurent polynomial ring by the usual polynomial ring. And so you can either glue things together, this works in the same way, or you could do things globally using the Cox coordinates on a toric variety. So somehow the natural way this works, the natural world in which this whole story works is to talk about subschemes of toric varieties. In some sense, F1 geometry is naturally almost the geometry of, one slogan way to say it is it is toric varieties over no field. And so we're sort of, the natural place this lives is for subschemes of tropical toric varieties. But all of the work and all of the difficulties already work for subschemes of a torus.
Diane, I guess you'll get to this maybe at some point, but not every tropical ideal can be lifted to an ideal. Is that correct?
That is correct. Yes. In fact, that might be the next slide. Or slide after next. Yeah. So let me tell you what we know about them. Okay, slide after next. I'll come back to. So this is all joint work now with Rincon at Queen Mary in London. So the first piece is, if I start with a tropical ideal, then I said that when I said, well, it's good enough to define the schemes in this way, but I want its variety to look like the tropicalization. And this is true. Okay, by what do we mean by that? It is the support of a polyhedral complex whose maximum dimensional cells are balanced. So this is this condition, the balancing condition I alluded to earlier. And the balancing is one of, I think, people who might have heard version of the story before. We knew polyhedral complex a long time ago, but balancing is just new from last year. That turned out to be much harder to prove. And we'll say tropical ideals obey the weak Nullstellensatz. So if the variety of I is empty, then the ideal is zero. Okay? Usually weak Nullstellensatz, right, is if the variety is empty, then 1 is in the ideal, 0 is the tropical one. Okay. In progress with Felipe again, and maybe I'll say one sentence about that at the end. And we also have, we now think we have a version of the strong Nullstellensatz as well. But I should say this is false if you don't put this tropical ideal condition on. So if you look at the variety of x plus 1 and x plus 2, just in one variable, so tropical one-dimensional torus, you need the minimum to be achieved twice here, in x and 1, so x has to be 1. But you also need the variety to be achieved at least twice here, so x has to be 2. But x can't be both 1 and 2, so that means the variety is actually empty. But if you look at the ideal generated by x plus 1 and x plus 2, because there is no subtraction, every polynomial in this ideal contains a term involving x. So it is not the ideal generated by 0. Okay, so the Nullstellensatz is false for all ideals, but it's true for tropical ideals. So tropical ideals obey the ascending chain condition. So there's no infinite ascending chain. I1 contains I2 and contains I3, etc. of tropical ideals. Sorry, it's a typo. I should say of tropical ideals there. Somehow I managed to erase that. And this should seem a little strange to you, because I told you earlier that the semi-ring of tropical polynomials is not Noetherian, right? That we can have these infinitely generated ideals. And in fact, even tropical ideals tend to be infinitely generated. So the example I gave you of an infinitely generated ideal is actually the tropicalization of an ideal. So this is not a contradiction though, right? Even though these two different versions of Noetherianness are very, very similar. Because what we're saying, there are infinite ascending chains of ideals. It's just that in any such infinite ascending chain, only finitely many of the ideals can possibly satisfy this tropical ideal condition. If we're in the homogeneous ideals, we have a Hilbert polynomial, so we have a definition of dimension. And it turns out the variety will have dimension, the maximum dimensionable cells of the variety will have dimension equal to the dimension of the ideal. And then to answer the question that came up before, there are tropical ideals that are not of the form, the tropicalization of an ideal for J starting from some actual ideal in the polynomial. So these are the motivating examples, but most of them aren't. And I think, I guess most, there's a sense in which we would expect most are not, in the sense of under the hood, there's a lot of matroid theory, and we know that most matroids are not realizable, not representable, and that for the same reason, we think most tropical ideals will not be of this form. And this is a bug or a feature, but I think in general it's good, because the question of understanding which ideals are tropicalizations is sort of impossible in a certain well-defined logical sense. So having this broad, slightly wider class of ideals that we can deal with makes it a more tractable theory that we might possibly be able to prove theorems about. I'll just observe that this is a result of Jan Draisma and Felipe Rincon, that there are balanced polyhedral complexes that are not varieties of tropical ideals. So it's fairly common in tropical geometry to just refer to a balanced polyhedral complex as a tropical variety. But this is saying not every balanced polyhedral complex has a tropical scheme structure. So there's something between all balanced polyhedral complexes and tropicalizations of varieties, perhaps, that have tropical scheme structures, which are the things we should really think about. But we don't know. I think we know, other than knowing that that it's not everything, we know very little about which polyhedral complexes have tropical scheme structures. So maybe in the interest of time, I should stop there. So, I could say a few more words about the updates, about the newer points, but maybe it's best to stop there. So thank you. Happy for any other questions.
If you would like to take some more time since we started late, that would be fine. It's up to you.
Okay, so I have a couple more slides. So maybe I'll say a few. Maybe we'll say a few words there. So maybe the first thing to say is the strong Nullstellensatz. So the sentences, for the longest time we didn't believe this, but I think this is work in progress, so that's why there's an asterisk here to say that this is maybe half of it we have written down and read carefully, and the other half we believe we know how it works, but we're still working out the details. But the asterisk is, if you're watching this years later on YouTube and this is not the final theorem, you were warned. And so the classical strong Nullstellensatz I would have phrased as saying, if the variety of I is contained in the hypersurface given by F, then F to the M is an I for some M greater than B, for some M. So, of course, this is assuming that my field is algebraically closed. It's the same as saying F is in the ideal of the variety of I. So this is the statement, ideal of the variety of I is the radical of I. The tropical version of that, which we believe is also true, is to say if I is a tropical ideal and the variety of I is in the tropical hypersurface defined by F, then some power of F also lives in the original ideal. And again, this is very false if we don't have the tropical condition. So this picture is meant to illustrate what this means. Perhaps these green dots might be my variety of I, and then I can fit any tropical variety I like through it. So I've chosen this tropical curve that passes through these dots. And then what I'm saying is that I take the tropical polynomial that defines that curve, and I'm saying that I know that some power of F lives in the ideal already. And the idea is the bit that we know for sure is that if I have F in this kind of convex in some sense, what do we mean by convex? We mean that all of its coefficients are as small as possible. So to relate it to the question we had earlier, the coefficients are as small as possible to define the same function. So we had a question earlier about the difference between, for example, x squared plus 0 and x squared plus x plus 0. And I would say x squared plus x plus 0 is convex in this sense. The coefficients are as small as possible. And then there's some work of Grigorov and Podolsky about variants of the Strong-North-Stern Satz just in tropical algebra, not trying to connect to geometry quite as well. And so we pull their results should pull across to give a strong North-Stern Satz in this way. And maybe the last thing I want to say is just to talk about the balancing condition very quickly. So the balancing condition is this sort of engine for tropical varieties that let us make these connections with cohomology and the of toric varieties and things like this. This idea that we're going to assign weights to the top dimensional cells so that the sum of it satisfies the zero tension condition. So you're meant to imagine a tug of war game where people are pulling with weight M1 from position U1, weight M2 from position U2, and then we have a zero tension. The sum of MI UI is 0, so no one wins the tug of war game. So if we're looking in the realizable case, if I start with an ideal in a usual polynomial ring or not polynomial ring, one way to define the multiplicities uses Grosvenor theory. So you pass to an initial degenerations and compute lengths of certain subschemes there. This you can also define for tropical ideals in the series ring of tropical polynomials. And so you get a definition of multiplicity, and then to show that this definition of multiplicity makes the tropical variety balanced, it turns out, and maybe this is just to advertise a bit of the proof and or to put a challenge as well, the hardest part of the proof, so we have a proof, but in some sense I feel it's not the proof from the book, is to prove that when I is zero dimensional, the sum of the multiplicities of the points are the degree of an ideal. If you think about it, classical projective geometry, if I have a bunch of fat points in projective space, the sum of their multiplicities is the degree of the variety. And just trying to prove that in this tropical context turned out to be much, most of the rest of the proof of balancing went through with the same proofs, and then this turned out to be much, much harder. And I think if anyone is interested in this, this is the sort of place where we could use some help to really understand what's going on. So that's just to give some ideas of the new things from the last year or two. So, yeah, I should actually stop there. So, but thank you for your attention, and I'm happy to take any more questions.
Let's thank Diane for a very engaging talk. Audiovisual team, would you please enable online participants to unmute themselves? Questions?
I have a question. Is there a notion of primary tropical ideal?
Yeah, that is actually the question. Yeah, I'm trying to finish a grant proposal this week where that is one of my questions in the grant proposal. so the ascending chain, so some of it, this is what we thought at first, right? This was one of our motivations, was to say, let's see if we can understand primary decomposition. As you may know, there are these weird examples where for varieties where you don't get irreducible decomposition of varieties, and or you don't get unique irreducible decomposition. And our first experiments made us think that thinking about things more from a more commutative algebra point of view would get rid of it. Now, the fact that we have the ascending chain condition means that every ideal can be uniquely written as an intersection of irreducible ideals, in the sense of irreducible in the sense that they can't be written as the sorry, not uniquely, sorry, I should be careful. The fact that we have the ACC means that every tropical ideal can be written as the intersection of irreducible tropical ideals, where irreducible means they can't be written as the intersection of larger tropical ideals. But the problem is uniqueness. And the issue is that the intersection of tropical ideals is not necessarily a tropical ideal. And so the usual, I mean, there are certain bits, you look at the usual basic definitions of primary decomposition and primary ideals, and it doesn't quite work. So there's something, this is something that is, I think, almost the next problem, because we don't understand this, and we don't quite understand the right definition of irreducible, in fact, because the only ideals that are both prime and tropical ideals are ideals of points. So somehow even prime ideals are the wrong things to define irreducible subschemes. But knowing what to replace them by is I think open at the moment. But very, very interesting.
Yeah, thank you.
Other questions?
So I probably missed the initial ideal thing. So how do you define multiplicity in terms of initial ideal?
So classically, for ideals in usual polynomial rings, what do? I take my W, so I take my vector in the interior of a face.
Right.
Looks like this U1. I then take the initial ideal with respect to the weight vector given by U1.
Okay.
And it turns out that this will be well, let me define it for you more geometric. You can give an algebraic definition in terms of a length of a module. Let me give it geometrically. It turns out that the variety of the initial ideal will be a union of subtori. If you're lucky, it'll be a binomial ideal. It'll just be one subtorus. But in general, it will be a union of subtori, and the multiplicity is the weight of that counted with multiplicity. So we're just, you think about passing to an initial ideal as a degeneration of your variety along a subtorus. And in the limit, it breaks into a union of smaller, it breaks into a union of subtori, and the multiplicity is counting how many of them.
Okay, yeah, thank you.
Other questions? Online audience? Please unmute yourselves if you want to ask a question, or you can type it in the chat box.
So one potential application of this seems to be to define tropical analogues of some classical non-reduced parameter spaces or moduli spaces like Hilbert schemes and so on. Yes. So yes. that has not been carried out, not to the best of my knowledge. Can you please comment on that?
That's yeah. So exactly. I mean, this is again something I want to do in the next year.
Yeah,
I think it's exactly. So there is a complication is that so we have some preliminary notes on the tropical Hilbert scheme. A problem is that it won't be. Well, I think this is one of those things that, I'm about to say something's a problem, but then I'm going to try and convince you that it's not a problem. It will be some object that doesn't look like it's finite type. It's going to look like it's horribly infinitely generated, but I think it's okay. It's somehow the tropical Hilbert scheme. You could almost think about as something that it will sit between the Berkovich analytification of the Hilbert scheme and the Hilbert scheme, right? So if you think about we shouldn't be too scared of things starting to look ugly, because anything that is more finite than the Berkovich identification is already a win in this world. Yeah, I completely agree. This is something, and what I hope is that this will sort of shed light. Understanding the Hilbert scheme will shed light on a bunch of other, all of these related questions about which subvarieties are realizable, and which things show up as tropicalizations and questions like that.
Thank you.
So since the question of moduli spaces came up, I have a question. In traditional algebraic geometry, if you want to study moduli spaces, you take a functor of points approach and then ask if that thing is representable. So is there a functor of points approach to thinking about tropical schemes?
So I think, this is very related to the previous question, in at least the partial work we have about the Hilbert scheme is to think about, is exactly to describe a tropical Hilbert scheme as a fine moduli space, so via a functor of points. So one of the issues, though, one of the things that slows us down a little bit is all of this world is defined. I mean, I've been telling you the story where R bar is the tropical semi-ring. You can replace this, the underlying technology, this valuated matroid story, works for all additively idempotent semi-rings, but an example, or maybe semi-fields, it doesn't let you define things automatically for things like families over an affine line or something. So families over more interesting bases are something that we still have to understand a little better in this world. So what to replace valuated matroids by? Somehow valuated matroids are tropicalizing something that's over a field, and we have to understand what to do for more interesting bases. So there's a piece of combinatorics that is still slightly missing, but in principle, absolutely, you're asking the questions that I'm also asking at the moment. And I think that I'm optimistic that these are questions that we will resolve over the next few years. And this is a team effort. If anyone who is interested in getting involved in these questions, and feel free to talk to me.
Right. I had in mind, I was thinking of something along the lines of, Hakim and then Toen and Vakeh had this very abstract notion of geometry relative to a symmetric monoidal category, where you fix some symmetric monoidal category and then look at rings, rings in that. So I think F1 geometry also fits within this framework.
Exactly. I think this is, I have to admit I'm not fluent in their work, but my understanding was that when you restrict their thing to this sort of world, to schemes over this tropical semi-ring, you get the same as the Loschide world, more or less. But yeah, sorry, go ahead with the question.
So yeah, the question was just, you could take these semi-rings and they would be like commutative algebras in some suitable category. So, you could try to define something along those lines. I was just wondering if that.
Yeah, so I think in principle that works. So this, this is why when I pointed, I think the work of Oliver Loschide has been the version of this sort of F1 semi-ring scheme stuff that seems to be best suited for the sort of stuff we're trying to do here, in terms of being the right mixture of tractable but having enough having enough abstract words. Like I know things like tensor products and things working was one of the difficulties in his world, and I think under the hood and some of these other things. But I don't rule out that some of these other versions of F1 geometry, like the term back here, etc., might be the right thing to connect.
I see. And a related question is: so these tropical ideals, can they be characterized categorically in terms of maps between between semi-rings? For example, like ideals of rings are things that occur as kernels of morphisms of rings.
Yeah. So we don't have a perfect description. We don't have a description like that at the moment, but there might, yeah. It's possible that there is a fairly elementary description like that, but we don't know it. There's some sort of, again, it's sort of hidden with these. I mean, it's maybe easier is to describe the bend congruence of a tropical ideal. I think that's the thing that might have a reasonable description, but that isn't something that anyone has worked out at the moment. But yeah, I think that would be interesting to know, and I agree, probably useful to know as well.
I see. Thank you. Other questions or comments? Questions from the online audience? Questions, comments, or remarks? If not, let's thank Diane again for a very nice talk.